Hi and welcome back to another Shouting Electronics. Today on the workbench we have got this pulse splitter. 24 volts AC or DC input pulse splitter. Let's first explain what it does and then we can see why it's not working. Okay, so this pulse splitter has one pulse in and two pulse outputs. Basically, in this specific pump house that this was installed in, you've got your water meter, and on the water meter itself, the water flow meter, there's a little magnet that spins around in a circle, and then every time it goes past a certain point you have got a, don't know if you can see it too well, a reed relay. That's a little piece of glass basically. Every time the magnet goes past it, inside the glass the two contacts touch together, and when the magnet moves away, they split up. So that basically gives it a pulse to say every so many liters has gone through the water meter. Okay, so that's fine because there you can take it straight into your control system, say your irrigation computer system or your pump controller. So it would let the irrigation computer know basically how much water is going through there, so it knows, okay, it is irrigating and how much dosing of the chemicals and the fertilizers and that to put in. Or the pump controller, it's handy so I can see, okay, I am running the pump but there's no water flow, so something's wrong, I must shut down under a safety. Okay, but now if you want to run both of these things, you can try bridge this onto both the inputs, but it's not the best solution. The best way is to actually isolate it. So what will happen basically, here is our reed relay by the water meter. It goes into the pulse splitter. And then it's got two more reed relays. Basically it's a coil and the reed contacts, and it goes out like that. So in this pulse splitter, it takes power in, okay, or 24 volts AC, converts it to the 12 volts that the circuit runs on, and then this reed switch here controls a transistor, which basically just pulls in these two separate coils for these reed relays, and then gives out two separate signals, one to the irrigation computer and one to the pump controller, whatever you need. You can just put more of those reed relays in and you can do lots of channels, but they only needed a 2-channel. So let's take a look at what this one is doing. Basically when it was on site, there was a power surge which destroyed the 24 volts transformer, as well as melted down the coils in contactors in there. And then once we replaced the transformer, we found out that this thing wasn't lighting up its power light. So let's go and pop it open so we can see. Okay, so let's just pop the board out there. Okay, and this is a very how you doing job, as you can see. This is basically how it was supplied to the customer. That this is the little switch mode power supply board, which takes the 24 volts AC, or by this time it's rectified, half-wave rectified DC, turns it into the 12 volts, which runs, there's our little transistor over there, and there's our two nice little 12 volt reed relays. I know they're 12 volts because I did get the data sheet for them. Those are the COTO reed relays, the 9007-12-00, which is a 12 volt DC coil, draws 12 milliamps on the coil and can switch 500 milliamps on the contact. So that's quite a bit, just for a little wetted reed contact, or not even wetted, just for a simple reed contact. Okay, so let's just go through roughly what's happening on this thing here. Okay, I'm going to hook up, see if I've got power here. Yeah, as you can see, I've I'm just running it off a 19 volt laptop power supply, which is fine because this is a buck switch mode converter, so it will lower it down to the 12 volts. Now, as I say, there was no lights running on it. So I think switch mode is a bit of overkill for this basic situation. That's just my opinion. Okay, so let's take our tester. Oh, okay, something I forgot to mention. On site, this runs on a 24 volt AC transformer. Here I am running it on a 19 volt DC laptop power supply, which doesn't make a difference because this is an AC and DC input, and I'll show you why in a while. Okay, so you see there, input I'm getting 20 volts, 20.5 volts, okay? And yes, this wire was on, it's just my moving it around that caused this wire to pop off now. Okay, so now I'm going to test on this little switch mode board from the black to the red, which is the power in, and as you can see I'm getting 20.3 volts, and the out, which is the white, and I'm getting nothing. Okay, so let's pull off the load wire off this board here. Just restart it. Because sometimes if there's a short on the rest of the circuit, which I doubt it, then this switch mode board will actually shut down and not produce any output. And for those that want to know, L5973 chip. Okay, the L5973 is a step-down monolithic power switching regulator, so it can deliver more than 2.5 amps. So to me, this thing looks kaput, broken, dead as a doornail. Have you ever known any live doornails? Now, let's show you basically the power circuit on this thing. Okay, so you got your AC input there, 24 volts AC. One pole of it goes through this diode, don't know if you can see that diode there, which acts as a half-wave rectifier. And then the other one goes straight through so there's the switch mode board, there's your, well, they turn that into the ground, and then it goes out to the rest of the circuit. Okay, so your input to this diode from your transformer is basically just that. Okay, after the diode, we're going to be getting something like this because it's cutting off the lower parts of each waveform. That's a half-wave rectifier. Okay, but then later on in the circuit, they've got a nice capacitor. 470 microfarad. So then after that capacitor there, your waveform now goes down a bit. Now it looks like that. So it's mostly positive. I hope you can see that on the well, it's completely positive. I hope you can see that on the video. And it's just a bit rough. And then this powers the rest of the circuits. Now what I'm thinking is this is a bit of overkill because this circuit really doesn't draw much. Let's work it out how much it draws, okay? We already said that our two relays, their coils draw how much? 12 milliamps, okay? That makes it 24 milliamps. It's got LEDs on the front. What did I just drop? Okay, it's got two LEDs there. If both the LEDs are running, let's see. They're running through those small resistors there, which are 1K resistors. Okay, so let's say that just for rough sake that they are LEDs has got a volt drop of 2 volts, okay? So we say our 12 volts that the circuit operates on minus 2 volts equals 10 volts, okay? Now we need to use Ohm's law to calculate the current, okay? Ohm's law, V I R, you know that triangle? Okay, so if we want to find out the current that those LEDs draw, we have to cover up our eyes. So we got voltage over resistance, okay? So we already said we got 10 volts because the LEDs are drawing 2 volts. So we're dropping 10 volts, okay? Divided by the resistance, which we said is 1000 ohms per LED, equals 0 times 0, or 0.01, which is 10 milliamps per LED, okay? So let me say 2 by 10 milliamps equals 20 milliamps, okay? And then that makes 44 milliamps. Okay, that's very little current. I'm not counting the quiescent current in the transistor or anything like that, because that's nominal. We're going to see why I'm working this out now, to see what we can do instead of using a switch mode regulator, which is more susceptible to surges and things like that, especially because this is out on a farmland. Your power isn't too stable. Okay, so now I'm thinking, let's put a linear voltage regulator in here. In my hand here, I don't know if you can see it, I've got a 78M12, okay? 78M12. Okay, now we want to see, can this handle the power requirements of the circuit without needing a heatsink? I say it can, but let's just do the paperwork just so we know it can, okay? So this, if we look at the data sheet for the 78M12, okay? Maximum voltage in, 35 volts DC. Okay, that's maximum voltage in, so that's fine because we're 24 volts rectified, so we're about 30 volts maximum or so. The voltage out is round about 12 volts DC, that's okay. Now we're looking at the TO220, because that's the one that I've got here. That's a transistor casing, okay? Let's look at the data sheet, okay? Junction temperature must be between minus 40, depending on which data sheet you look at, up to 150 degrees centigrade. So if our junction temperature goes up to 150 degrees centigrade, this thing's going to start shutting down. And it's going to get very hot in there. Now on the data sheet also you got the thermal resistance from the junction to ambient, okay? So that's from the center of the transistor to our ambient, to basically our air, to the outside of our case. Not to the case, but to whatever's getting conducted outside the case. And that, in this case, is 60 degrees centigrade per watt. So if we're pulling 1 watt through this regulator, we're going to have a temperature difference of 60 degrees between the die in the middle and the outside of the outside case, okay? But we don't want the junction to go more than 150 degrees. So that's what we're going to work out now. We've already worked out that we're 44 milliamps, okay? So let's work out the power dissipation. I don't know if that PDIS is right, okay? Equals V in minus V out times your I out, okay? So we set our voltage in. Well, it's a 24 volts, but we are rectified. Let's say 30 volts, okay? 30 volts into the regulator, okay? Minus, we want 12 volts out because it's a 12 volt regulator. Times our current that we're drawing, which we said is 44 milliamps, which is 0.044 amps, okay? So 30 minus 12 is 18 times 0.044 amps. And what does that equal to? That is 0.792 watts, okay? So let's say 0.8 watts, okay? Just to work. So it's equivalent to 0.8 watts, which is less than a watt, okay? So let's take our 0.8 watts times our junction resistance there, thermal resistance there, which you said is 60 degrees centigrade per watt. Okay, so now that's easy to work out. Okay, so that gives us 48 degrees centigrade. Okay, that's 48 degrees above ambient, okay, which we take as 25 degrees because that's our normal temperature here, around about, okay? So we take our 48 degrees plus our normal air temperature of 25 degrees, and you see we got 73 degrees centigrade. Okay, so if we're drawing our 44 milliamps, we've done the maths. It says our inside die temperature will go up to 73 degrees, okay? What did our data sheet say? Up to 150 degrees. So that is less than half of the rating. If we were getting closer to our rating, then I'd say put a heatsink on to give us more dissipation. But the maths works out so we shouldn't get too hot at all. We should be well within the range of the linear regulator. So I think what I am going to do, I'm going to strip out this switch mode little monster that's hanging around here. And all I will need really is a input capacitor, which I've chosen a 220 mic 35 volts. A capacitor for the output, which is a 104. It's just a small one. And remember, there is a bulk capacitor later on in the circuit there. And then I need my voltage regulator. And you know the voltage regulator pinout. I hope you do. TO220 7812 series. Volts in, ground, volts out. And also the tab is also grounded. So I need to connect, basically. I'm going to take the input, which is over here. I'm going to put a capacitor from the input to the ground. That's going to be that large cap. Capacitor from the ground to the out. It's going to be the smaller cap. And then that basically should be it. This thing should sit nicely in here and do the job, I believe, more stably than the switch mode power supply, because we don't need that switch mode reliability. So let's go. As you can see, the capacitor's held a charge there because it gave it a little spark. Okay, so here is the switch mode board. Let's just take a look at it on my hand. How do you know it's a switch mode board? It's got that switch mode driver chip that we looked at, and it's got the coil. Then we know it's a switch mode board. Okay, it's also got the two capacitors, a few resistors and capacitors to set the frequencies and that to determine the voltage, and it's got a diode there. Okay, so now we've got our three wires on our board here. We've got our in, we've got our out, and ground. Now I could really go and put this on another board or something, but I think this is going to work out just fine without having to do a whole power supply board and take up space on the circuit. We'll go overboard. We don't need to go overboard, do we? Nice if I had my little desoldering gun, yeah? Where are you? I lose more tools like that. I didn't like that thing flopping around in the breeze too much. How are we doing? Okay. So I'm just going to put it like that, really. Because it really doesn't need so much space, and when this thing's in its panel, it's pretty secure. Okay, so now I need to take a power. Can't explain this as I go. Okay, so there is my diode that's bringing my half-wave rectification. I did recently move houses, so can't blame me if I can't find half my stuff at the moment. You know how that is. I can't even find my little cutters. Okay, so that is going to be my input terminal. Burn my finger, burn my finger, burn my finger. Okay, the output terminal, as you can probably see from the diagram, that wire goes there, all the output on the board, but then it also wraps through to this terminal. I don't want this wire going under the regulator, so I'm going to actually just pull it out there and put the supply off there, or the output points. Okay. Okay, so that's output's going over there. Amazing. Now there goes my capacitor. Bye-bye, capacitor. As you can see, the solder's still wet there. Okay, so that's my in and my out. Basically, this circuit will work now. Because I've got my in and my out connected, my ground connected. But just to make it stable, you want to actually connect some capacitance. I'm not going to put this capacitor on here, I'm going to put it between those two terminals, because that is the negative to the regulator and the out of the regulator, which I said is going to be the small capacitor. Why don't you want two larger capacitors on the output of a regulator? because then it can't regulate too well, because say it's trying to bring the voltage down, but the capacitor's supplying the voltage to counteract it. So you just want a small one just to prevent oscillation and try to keep it a bit stable. I think I'll put too much on there, I don't know. Okay, so there's our capacitor. It's close enough to the regulator to give us the stability we need. Now just the capacitor. That needs to go on the input of the regulator. I've got plenty of room to put this capacitor vertically even if I wanted to. Because this just looks like a universal little case or whatever that I used. Electrolytic capacitor, so always observe the polarity. So if you'll see, I've put the positive of the capacitor onto the input of the regulator. Yeah. Whatever done. Okay, that's still in. Now I just need to take a little negative jumper. So a cat daughter cable comes in handy, man. Okay. And as you can see, I'm going to be soon needing a new reel of solder. Mantic! Yeah, so I got this roll of solder from, and this lasted me quite a while, so. Okay, how long is this taking me so far? Just over half an hour. Okay, so there we go. Our bulk input capacitor is in place. Our regulator, our bulk output capacitor. Okay, do we have a power light, guys? Yes, we do. Okay. Let's check our voltage before we go and button this thing up again. Okay, and that's clear on the screen there. Okay, so I'm going to check from the ground. I said you can use the center pin or you can use the tab on the regulator, okay? Volts DC, let's go down to 20. Okay, we know our input's going to be more than 20. Okay, you see, because we've got a bit of load on it now, our input's down to 19.8 volts. Output, 11.99. You can't get much closer than that with this system. So that's fine. So now, I'm going to pretend like I'm the read relay, or the read switch on the watermeter. So I'm going to short out these terminals. When I do, you should see the pulse light come on, and both these relays should click. So we get a pulse. I can't even hear it. cool beans. Okay, so this thing is ready. So I'm going to go button it up. And then sometime during the week I will go reconnect it in the pump house. Obviously I'll need another 24 volt transformer for it. And then it's good to go. There shouldn't be a problem there because that's nicely in place. And there we go. So I hope you liked that video. If you did, give it a thumbs up and subscribe to my channel. And click the little bell icon if you want to be notified in future when I upload more videos. Hope you enjoyed that one. Thanks guys.